Section 1110, the Taylor and Maclaurin series. So let's jump into this. Up to now, we've talked about general power series, finding their radius of convergence, their intervals of convergence, and then we got into this very specific power series where we said the power series from n equals 0 to infinity of x to the n is equal to 1 over the function 1 over 1 minus x, as long as, we should add in the caveat here, this is as long as the absolute value of x is less than 1. And then we manipulated that. We spent a whole section working with that and talking about how we can algebraically manipulate that function and come up with a corresponding power series, or we could even differentiate or integrate that function and variations of that function and come up with those corresponding power series. But not every function in the world can be written as some sort of algebraic or integration or derivative of 1 over 1 minus x, clearly. So we got to get into some more general problems here. So what functions actually do have power series representations, and how do we actually find them? So that's what this whole section is about. And we're going to create, as we go through this section, we're going to create a bank of useful power series. We have one already, the one that we have right here at the top, the x to the n, the power series of x to the n being equal to the function 1 over 1 minus x. But we're going to create a little bank of more excuse me, of more power series that we can utilize to manipulate and work with in algebraic ways, in ways where we utilize calculus, take integrals. And ultimately, our whole goal here is to get back to, and it's been a while, it took us a while to build up to this, but if we can think about that original problem that we have here, I had a little note here, so let me jump over here. That original problem that we had talked about, how do we do something? What if we wanted to do something like this? What if we wanted to integrate this, right? Question mark. How do I integrate something of that form, right? How do I get into that? How do I estimate that? How do I come up with that integral if I don't have integration techniques, right? We get stumped on, this is not an elementary integral. So how do I do this? Well, this whole section, this whole entire chapter, all 10 sections so far, it's been our biggest chapter yet in Calc 2 here. How do I get to a place where I can actually do this integral? So that's where we're headed. By the end of this section, we'll get there. And that's exciting for me, hopefully for you too, because we've done a lot of theory to build up to this. Okay. So let's jump into this. If we have an actual function and it has a power series representation, then it would look something like this, right? This is our definition of a power series, C sub n, x minus a to the nth. We're centered at some value x equals a, and we'll have convergence for x minus a less than r. Okay. So if that's true, how do we actually find those coefficients, right? That's the piece that we need to figure out. How do I find those coefficients? And so we're going to jump into that, and I set up some notes over here ahead of time just to get us going a little bit quicker on this video. And same thing I just had typed up there, but now we're going to do it and find those coefficients. So if we've got a function, we have a function f of x, it has a power series representation. So there's the key. We'll talk about how we determine that in a little bit here. But first, if we have a power series representation, then we know that the function looks like this, that the function is equal to c naught plus c1 times x minus a to the first plus c2 times x minus a squared, and on we go. Okay, so how do we actually find those coefficients? So I have to shrink this down a little bit here. How do we find those coefficients? Well, what we're going to do is we're going to start by taking derivatives. This is an infinite polynomial, so we can take the first derivative, f prime of x, and when I do that, the constant, of course, goes to 0. This whole x minus a to the first power becomes 1 times x minus a to the 0, so this becomes just c1 plus, and then we're going to have 2 times c2 times x minus a to the first, plus 3 times c3 x minus a to the second, plus 4 times c4 x minus a to the third, and then on we go. And the nth term, the nth term would then be n times cn times x minus a to the n minus 1. So we're going to look for some patterns here. So I'm going to take it out to that nth term. Then we're going to take the second derivative. So we're just going to keep going. We're going to take repeated derivatives here. And again, remember, what we're looking for is to determine what these coefficients are. So notice right here the c naught, and notice the c1 right here in the first derivative. And it turns out if into the function I were to plug in a, the actual point where we're centered, if I were to plug in f of a, right here, notice that all the other terms except for the constant would zero out. And same thing would happen here if I plugged in a to the first derivative. All the other terms would zero out and I'd have just that first constant. So something to notice here, we're going to come back to that in just a minute. We actually will plug in a's, but I want to develop the pattern with the derivatives here. So f double prime of a, if I take the second derivative, then I'm going to have 1 times 2 times, and I am going to write it out like that. I'm not going to actually simplify because I'm looking for the pattern, times c2 plus, and then I'd have 2 times 3 times c3 x minus a to the first plus 3 times 4 times c4 times x minus a to the second plus, and then dot, dot, dot. We do want to generate this pattern. So then we're going to have n minus 1 times n times cn times x minus a to the n minus 2. And on it goes. Okay, let's do a third derivative. So by the third derivative, I think we'll start to see the pattern pretty clearly by the time we get to the third derivative. I do want to notice that constant there. Okay, keep going. By the time we get to the third derivative, we're going to have 1 times 2 times 3 times c3 times x minus, the x minus a will be to the 0. So x minus a to the 0 is just 1, plus we'll have 2 times 3 times 4 times c4 times x minus a to the first, and out 2, and we're going to have n minus 2 times n minus 1 times n times c sub n times x minus a to the n minus 3, and on it goes. I think I ran off the screen there, but there we go. Okay, we could keep this going, right? We could keep taking repeated derivatives, but every time we take a repeated derivative, if we could focus in on this term right here, every time we take a repeated derivative, the terms in this expansion of the power series, we bring down the power and then we reduce the power by 1. And what ends up happening is this piece of it starts to resemble a factorial until we get all the way to the point where the x minus a, where the actual, we've taken n derivatives and we're doing n minus n, so that's 0. By the time we get to the nth derivative, what we end up with is we have a factorial in front of the coefficient that actually matches, the factorial matches the derivative that we've taken. So if we continue this down, we're going to end up with, by the time we get to the nth derivative, we're going to end up with n factorial in front of c sub n. Okay, so that's the pattern that we're starting to see right here. So what I have to do here is I have to make one little note, and then we'll solve for those c sub n. So let's just, because we want the pattern, this obviously this first right here, we haven't taken a derivative. And so what we want to do is we want to actually define that as the 0th derivative. That's kind of a funny way to say it, but that's a convention we use in mathematics to fit this pattern, and other patterns as well. So let's do this. Let's say, let me zoom in here. So let's let, actually, let's do this first. Define, before I do a let's define 0 factorial to actually be equal to 1, and these are mathematical conventions, so we can do that, and I'm not just coming up with that definition out of nowhere, and f of 0, the 0th derivative of x is actually equal to the function, okay? So these are mathematical conventions. All right, so if we define those two mathematical conventions, then let's go ahead and let x equal a. And notice what happens out in these derivatives. If I do that, the 0th derivative of a, which remember is actually just f of a, I just want to clear that up again from this definition, that is actually just the constant, c naught. And when I take the first derivative and evaluate it at a, and I think it just blipped off the screen. But when I take the first derivative and I evaluate it at a, I get just c1, the first coefficient. I'm sorry, well, yes, the first coefficient after the constant. So c0 is the constant, and then c1 is the first coefficient. When I take the second derivative and I actually plug in a, so the second derivative here at the top of the screen, notice when I plug in a, all of the terms that have x minus a in them still zero out. And so I end up with 1 times 2 times c2. By the way, that's the same, and the reason I haven't simplified it, that's the same as saying 2 factorial. And this one is actually 1 times c0, so let's write that as 1 factorial times c1. And let's take the third derivative. And when I plug in a, the third derivative is going to become 1 times 2 times 3 times c3, which of course is 3 factorial times c3. And if I keep going, so if I continue this pattern, dot, 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 what happens is by the time I get to the nth derivative, and that was up here, we were talking about this guy right here that I have in red. If I keep going, if I keep taking derivatives, by the time I get to the nth derivative, and I plug in a, so all the remaining terms aside from the constant at that nth derivative zero out, what I will have is n factorial times c sub n. Okay, well, now we can actually solve for those coefficients. So to solve for the coefficients, when we solve for the coefficients, it turns out that c0 is equal to f of a. It is also, I should add in what we've stated up here because we want to see the pattern. And so remember that 0 factorial is equal to 1. So this is actually, there's actually a 0 factorial right here. And so I could even say that this is f of a over 0 factorial. That'll become important when we see the rest of the patterns here. And c1 is equal to, if I can get it all on the screen here, c1 is equal to the first derivative at a over 1 factorial, and c2 is the second derivative at a over 2 factorial, and the third coefficient is the third derivative, c3 is the third derivative evaluated at a over 3 factorial. And if we keep going and we see that pattern there, the c sub nth coefficient is equal to the nth derivative of the function evaluated at a divided by n factorial. All right, so we have now come up with a way in which we can actually find those coefficients. If a function has a power series representation, then we can find its coefficients by taking repeated derivatives and evaluating them at the point at which we're centered. And so summarizing that, what that tells us is that gives us what is called the Taylor series for a function. And so let's summarize that here. So the Taylor series for a function, using, I guess we'll keep that on the screen since we know that. So the Taylor series for a function if we have a function. So if a function has a power series, if a function has a power series representation, at x equals a. So if it does, and again, we'll have to talk about which functions have power series representations, but if it does, if it has a power series representation, then that means that f of x is equal to the power series from n equals 0 to infinity of c sub n, x minus a to the nth, which would be c0 plus c1 times x minus a to the first plus c2 times x minus a squared plus on and on we go. Okay, for some values of x, right? This will be true for some values of x less than r, where we have a radius of convergence of r. And now the coefficients can be found by looking at the nth derivative evaluated at a over n factorial. So we're putting together our pieces from above where we're saying these coefficients now we could find. We could take repeated derivatives, we could look for the pattern, divide by n factorial when we plug in a, and that will actually give us our power series representation. So now we can take a function and we can write its power series representation. Whereas before we were looking at power series and figuring out when they converge, now we can actually create these power series by looking at these repeated derivatives. So that tells me that that is the Taylor series. So this is what gives me the Taylor series. If we were to actually expand this out and write it out, so the Taylor series, the Taylor series of f of x at x equals a in expanded form, if we were to write that out. So that's f of x is actually equal to n equals 0 to infinity, replace those c sub n's. It is actually the nth derivative evaluated at a over n factorial times x minus a to the nth. And we could write that out. We can expand that out. We could say, okay, so that's going to be f of a plus f prime of a over 1 factorial times x minus a to the first, plus the second derivative, f double prime of a over 2 factorial times x minus a squared, plus the third derivative, evaluated at a over 3 factorial times x minus a to the third, and on. That pattern goes. Okay? That is what is called the Taylor series of a function centered at x equals a, or at x equals a. Now we end up with a very specific type of Taylor series, and we look at this one an awful lot. And so what if, right, it turns out that the a that we look at, what if a equals 0? And that gives us what is called the Maclaurin series. It is just a specific, it's still a Taylor series, it's just when we're specifically at 0. So this is specific to being centered at 0, at x equals 0. Let's write x equals 0. And we do become centered at 0. We often want to look at functions expansions. We like to look at the function's power series representation where we actually are at 0, 0 being our center point of our rectangular coordinate system or x-axis. And so we do look at this an awful lot. And so this is the specific term, the specific word we talk about, Maclaurin, and Maclaurin series are centered at 0. So what if a equals 0? Well, then we have what is called the Maclaurin series of f of x. And again, just a specific Taylor series. So the Maclaurin series of f of x at x equals 0. So being specific to the 0 here. And so that gives us a function f of x. That would be the power series from n equals 0 to infinity. This time when we're looking at those derivatives, we actually are plugging in 0 and over n factorial. And it's just going to be times x to the n because it's x minus 0. So when we look at a Maclaurin series expansion, it's going to be f of 0 plus f prime of 0 over 1 factorial times x plus the second derivative evaluated at 0 over 2 factorial times x squared plus the third derivative evaluated at 0 over 3 factorial times x to the third, and so forth. Okay? So that gives us a specific series called the Maclaurin series. So when we're centered at 0, we call it the Maclaurin series. Or if we're asked to find a Maclaurin series, we would know, okay, that's centered at 0. All right, so that is the general theory behind Taylor and Maclaurin series. But what is, right, we were very specific right here, and we said if a function has a power series representation. So how do we know if a series has, if a function has a power series representation, right? Because if it does, we'll be able to find it using this process, take repeated derivatives, look for the patterns, and generate a power series. But how do we know that we can do that? Well, that gets into some remainders, and that's what I want to talk about right here to end out this video. So before we do, summarize what I just wrote up over there right here in this typed form, and I'll post this in typed form for you guys as well to reference. But this is just what we just went through. We just generated this pattern. If we have a function that has a power series representation, we can find its coefficients by looking at those nth derivatives and evaluating them at a over n factorial. And then that generates our two specific series, a Taylor series, where we're centered just at the generic x equals a, and then the Maclaurin series when that a is equal to 0. So we have our two definitions, I guess, Taylor series and Maclaurin series. Maclaurin being just a specific type of Taylor series being centered at x equals 0. All right, so very quickly, just to talk about when can we actually do this process? When can we write power series for functions? And so what functions will have these power series representations? How do we prove that we can actually find a power series representation? So I'll just walk through this pretty quickly here. If a function has derivatives of all orders, meaning we have, and we have a power series representation, as we've talked about before, then the function itself would be equal to the limit of its partial sums of this convergent power series. So we define what are called the nth order Taylor polynomials. So the nth order Taylor polynomials, that's a partial sum where we're looking at the power series from I equals 0 to n. So we're actually looking at a polynomial, right? A polynomial of nth degree. So that creates a polynomial of nth degree. If the function itself then is the sum of these Taylor series, then the function is equal to the limit of these partial sums. So this is a limit of the partial sums. So the function itself is a limit of the partial sums. Going back to just definition of what does it mean to be a convergent series? Well, if this power series is converges to this actual function, then it must be equal to the limit of its partial sums. And so if we used a finite Taylor polynomial to actually approximate the function, then we would have some remainder. So the function minus its Taylor polynomials would be equal to some remainder. We call that R sub n. So the remainder of whatever, if we've made an approximation with a partial sum, the remainder is going to be the difference of the actual sum. So this is just using, our remainder definition has always been this. The remainder is just the value of the sum minus the partial sum, but we're talking about it in terms of Taylor polynomials now. So that remainder is what the error is. That is the error between a Taylor polynomial, a partial sum, a finite sum, and the actual function. Okay? So the error in using the nth partial sum to approximate the function. And so the function itself must just be equal to its Taylor polynomial plus its remainder. That's just how we define infinite sums. Okay, that said, then we have a theorem that says this. It says if we have a function, so I had to define all that notation before I could give you this theorem. So the theorem says this. If we have a function and it is equal to its Taylor polynomials, t sub n, plus its remainder of using that Taylor polynomial, then if the remainder itself, so here's the key, if this remainder goes to 0, right? Sorry, I used the wrong, I wanted to use the highlighter there. If its remainder goes to 0, we'll use a highlighter and we'll circle it. If the actual error goes to 0, then the error in using a Taylor polynomial is approaching 0. If the actual error approaches 0, then the function must have a power series representation. So that tells me that the actual function must, if that is true, then the function f of x must have a power series representation. So if we can show that that remainder goes to 0, then we know that a function has a power series representation. Okay, so that's the type of functions that we're going to be able to write power series representations for. Now, in general, showing that this remainder goes to 0 can be a difficult process. So, I go through that theorem because I want you guys to understand the theory here, but in general, we are going to make this assumption. We're going to assume that the functions we're looking at have power series representations. So we are going to assume that, and we're going to focus more on the mechanics of generating those power series representations and utilizing them than we are on showing that we can actually prove that a function has a power series representation. But this is how you prove it. You basically just show that the remainder goes to 0. And we've worked with remainders, so hopefully the general idea here can intuitively make sense to you. If the remainder goes to 0, then of course the function's, the function must have a Taylor series representation. Okay, our video here has gone upwards of 20 minutes, and I'm going to end it here with a theory. I was going to try to squeeze in an example, but that's going to be too much. So I'm going to go ahead and put the examples in separate videos, but this is the theory. This is where we're going to go. We're going to focus in on figuring out how to represent those functions as power series. And by doing that, we have to take derivatives, repeated derivatives, to figure out what those coefficients are. So we're going to look at some patterns as we go here.